Okay, so hi there everybody. We're now in our next video on number theory, and today we're going to talk about the continuation of our least common multiple. Okay, so our least common multiple has a simple remark after its definition. So the remark says, given non-zero integers, okay, given non-zero integers, we'll have the integers a and b, okay, a and b. The least common multiple of a and b always exists. And the LCM of a and b, the least common multiple, is at most or less than or equal to the absolute value of a and b. Okay, so again, the remark says, okay, based on our discussion, it's very clear that given any non-zero integers a and b, the LCM of a and b always exists, and the LCM of a and b is less than or equal to the absolute value of a times b. Okay, so furthermore, in this video, we're going to end this with a theorem. So what we lack actually is the relationship between the ideas of the greatest common divisor, GCD, and the least common multiple, LCM. And this gap is filled by this theorem over here. Okay, so this theorem says that for positive integers a and b, okay, for positive integers a and b, the GCD of a and b times the LCM of a and b is equal to a times b. Okay, again, the GCD of a and b times the LCM of a and b is equal to a times b. Just kindly check on your modules. Maybe I wrote there an equal sign over here. So kindly change that. Okay, I'm sorry about that. Okay, so anyways, it's times, it's multiplication. Okay, but if you want, you can put a raised up there. So let's provide a proof for this. Okay, proof. Now to begin our proof, we will let D be equal to the GCD of A and B. Oops. And we will have and A equals D times R. Okay, because D is a multiple of A. Okay, D is a multiple of A given this certain R. And B is equal to D times S. So also D is a multiple of B given this certain S. We'll have D. For integers, for R and S in the integers, shall we say. Now, if we let some certain M be equal to um, A times B over D, we can also write this actually as A times B divided by D. So then, what we have is M is equal to A times S, which is also equal to R times B. Now, how did we get this value? Take note from A over B, A times B over D here, so we can get these values. How? Recall in this equation over here, we can get the value of R. What's the value of R? R is equal to transpose the D to the other side. That's A over D. And here we can also get the value of S. Transpose the D to the other side, so we have B over D. So using these values of R and S, okay, notice that M is equal to RB. Why is that? Because B over D is equal to R. Notice this part. This is equal to R. So if this is R, so we have, um, yeah, we have RB. We have RB. Okay, sorry. Again, RB came from R, rather, this is our R. R is equal to A over D. I think A over D. So again, I'm sorry. We have here A over D. Okay, so this becomes your R. R and B is RB. For the other way around, we have our S. Okay, I'm referring now to the S. Our S is equal to B over D. So here we have B over D. This is equal to our S. So therefore, we have A times S. So that's why we have AS. So all of these are values of M. Okay, values of M. Okay. This effect actually, the effect of this is that M, okay, we have made M as a positive common multiple of A and B. Thus, or that is, shall we say, M is a positive common multiple of A and B. Okay? Now, after this part of the proof, we will now we will let another variable C, okay, be any part of positive integers that is a common multiple. Um, no, that is a common multiple of A and B. Okay, and say for definiteness, actually what we're going to do is just to follow all this reasoning here above. Okay, using this same reasoning above. Okay, so for definiteness, shall we have that so that we can have safe space? Um, say for definiteness. Okay, we will have this C. Since we said that C is a common multiple, and here, actually, the effect here is actually to we just wanted M to be a positive common multiple. So therefore, M is equal to ASRB, right? So this is the important part, actually. Since we know that M is a positive multiple of AB, M, okay, M is a positive common multiple of A and B. Therefore, we have this equation. M equals AS equals RB. Here, we stated directly that C is a positive common multiple of A and B. So therefore, by that, it should have this equation also, some sort of equation. So we have C is equal to AU equals BV. Okay? Now, as we all know, okay, as we know, there exist integers. So let's write that. As we know, there exist integers x and y, okay, such that we can have the greatest common divisor, the GCD, okay, to be equal to a times x plus b times y. Okay, so our greatest common divisor can be um, a times this certain x and b times this certain y. So in consequence, we will have this series of parts. So let's say C, okay, over M. Okay, C over M. So meaning we can say that M divides C. So from this, we can say that we know the value of M, right? M means here, AB over D. Let's write it down. M equals AB over D. I tried to fit that on the screen or make it over above. Okay, there. You can see that M is equal to AB over D. So this is equal to C all over AB over D. Okay. Now I want to make this is a complex fraction right now. I just wanted to make it a simple fraction. So let's make it get the reciprocal of the denominator multiplied to the numerator. So we have CD over AB. Okay. So also we know D, the value of D is over here. D equals AX plus B. So let's substitute that. C times AX plus B, Y rather, all over AB. Now we want to distribute the C to all the parts of AX plus BY of D. CAX plus CBY all over AB. And then we will want to, cancel out what we can cancel. So we can say that CAX, or let's put it next line below. Let's put it over here. CAX over AB plus CBY over AB. And then if we do this, we can cancel out actually the A's here, cancel out the B's here. So what we'll have is CX over B plus CY over A. And we want to group together all the others, okay, so that we can have the X and Y alone. So we can see that C over B of X times X plus C over A times Y. Now, if we're going to go back to the definition of C here, okay, of C here, okay, we can see that, C over B is equal to V. Okay, if you want, let's write it down here. Um, Let me write it out again. C equals AU, or maybe I'll use black. That'll be visible. C equals AU equals BV. Okay, so what's the value of U? U is equal to, isolate U, so we'll put A down below. So we have C over A. How about V? V is, isolate V, so we have C over B. So substituting here, we have C over A is U, C over B is V. So therefore, what we have is, let's put it here, C over B is V. We have Vx plus Uy. Okay. Now from this equation, we can see that, Vx plus Uy ends up in in this um this form. Okay. So simply this equation states that we want, since it's GCD, so this equation states this equation states that, M is a factor of C. So we can see here M is a factor of C because it ends up in a greatest common divisor form. Okay, so we can say that M divides C. Okay, allowing us to conclude that M is less than or equal to C, right? Because M is only a factor of C. Okay, meaning it's understood that it's less than or equal to C. Okay, if they're talking about, multiplying it by 1. Okay, it can be equal to or it should be less than. Okay, so thus from here, so thus, in accordance, okay, with our definition of LCM, with the definition of of LCM, okay, M is equal to the LCM of A and B. Okay, M is equal to the LCM of A and B since it's the least, it's lesser than C. Okay, and then, so that is, we can therefore then say that is, remember that M is equal to the LCM of A and B. Okay, or maybe we can put M over here. Let me change that. LCM of A and B, the LCM of A and B is equal to M. We can remember above that M is equal to AB over D. It's over here. AB over D. AB over D. So let's write it down. M is equal to AB over D. Oops. AB over D. And we say that also, we know that D, okay, is the GCD of A and B. So therefore we have AB all over the GCD of A and B. Okay? Okay, which is, from this equation, I think we can derive now that what we want to prove in the first part. Okay, how can we do that? Um, Transpose this GCD to the other side. Further, that is, hence we have a GCD of A and B times the LCM of A and B is equal to A times B, and which we want to prove. Okay, hopefully that's clear. What we will do actually is to um, take a hold of these equations, these specific equations. We have LCM of A and B equals AB over GCD of A and B. What we want to do is to transpose um, this here by cross multiplication. So if we do that, what we'll have is the GCD of A and B times the LCM of A and B is equal to A times B, which is the one we want to prove. Okay, so thank you very much for watching. I hope you learned something from here. I will also hope that you will click the like button and then subscribe to my channel. And yeah, thank you very much for watching. Okay, I will see you soon in the next coming videos. Okay, see you.